Okay, looks like my memory space caught up with me there at the very end, so I'm going to try to make a better effort here to keep the file size down. So in order for you to be able to do what you need to do regarding equipment, obviously external beam units are going to need uh, to be at the top of the list. You're looking at maybe adding an additional machine if your load exceeds about 30 patients a day. Generally, when you start adding on more than 30 patients a day, you're going to really start to eat into the expected life of your machine, more so than you might think. So having more of a balanced patient load can help save your machines. It's hard sometimes to make an argument to administration about that, but that's generally what you need to do. Obviously, brachytherapy sources are used in combination with external beams. Sometimes those are the best ways to treat certain uterine, cervical cancers, that kind of thing. That is also equipment that you will need to be able to maintain. A simulator, it's the role of the simulator is now more combined with the CT sim. From the CT simulator, most planning systems will be able to give you what's called a digitally reconstructed radiograph that will allow you to be able to position your patient, perhaps using other tools, CBCT, what have you, in order to be able to make sure that you're on target. So again, that's another quality assurance method that you can use. Dosimetric accuracy. For dosimetric accuracy, obviously you are looking to make sure that you want as accurate a treatment as possible. The problem with doing that is that you're looking for a little bit of tolerance in different things as you move along, and those differences in tolerances start to add up. Case in point here, you're looking at ion chamber. Obviously, if you're looking at different components or different steps as you go through, that uncertainty adds up. And this is just for the ion chamber. Once you've got the ion chamber and you put that in the process of trying to figure out what the dose is at a particular point in the patient, once you add in all of these other steps, then you start to see where you've got 5.6% uncertainty as far as what it is that you're delivering to the patient. So those things add up. And that's what a QA program is there to try to do, to try to keep those things within as good a tolerance as possible. That way, your uncertainty is not quite as high. Equipment specifications, obviously, you want to make sure that you've got the right equipment in order to be able to accomplish what you need to do. Those kinds of things are more of a conversation between the vendor and usually the person purchasing the machine. Obviously, the physicist is going to get dragged in order to be able to make sure that we have all the equipment that we need in order to be able to produce something. For acceptance testing, we want to make sure that the machine is doing what the manufacturer says it can do. For a linear accelerator, we are looking here at doing a radiation survey around where it's being put in. For the accelerator itself, we're looking for jaw symmetry, to make sure that the jaw doesn't have one end that's really, really down low and the other end really, really high. Want to make sure that all of that's set pretty well. For coincidence measurements for acceptance, collimator axis, light beam, crosshairs, light beam with x-rays. Again, you're looking at shots on film to make sure all of that checks out. Mechanical isocenter, collimator rotations, gantry rotations. Again, for the description made in the book, it's not going to be exactly what you're seeing on the more modern machines that are out there. It's not to say it's anything to sneeze at, but these pictures are going to be a little dated. The isocenter of the radiation, we're looking at collimator rotations again. The treatment table, gantry, all of those kinds of things. We're looking also at multiple beam alignment checks. If you have a half beam block, do you really have a half beam block? Those are the kinds of things that you'll be looking at. Multi-leaf collimators, MLCs, what could go wrong? Well, there's a lot that could go wrong. You're looking at the width at isocenter, calibration of the leaf positions. Are they actually getting to where they should be? Leaf travel, leaf speed, transmission, what's actually going through it when it's in the field, leakage, field shaping. Does it shape with the fields that you need? And trust me, there are going to be some really wacky fields out there. X-ray beam performance, how well do the energies do? Field flatness, how flat is the field? Again, you're wanting to deliver something that's fairly homogeneous. In other words, something that's straight, straighter than that, over a certain length. And that's what the field flatness is going to measure. You want something like this so you can make sure you're hitting the target the way you want to hit the target. And then when it comes to electron beams, you're looking at energies, you're looking at flatness and symmetry. And then you're also looking at monitor chambers. Are they checking things as they should be? Wedges, and then other miscellaneous checks. You also have radiographic simulators. Again, this is not something that you're really going to be looking at here as radiation therapists. CT simulators, a lot of times that's going to be handled more by a diagnostic physicist than it would be a therapy physicist. Not to say that they couldn't if they had the proper training, but generally that's where that's going to fall. And then you also have brachytherapy to make sure the sources meets the user specifications. You can see the tolerances here. Again, I'm not really interested in quizzing you on those because that's not really what your job is. You can also see here source identity, source uniform, and symmetry when it comes to the distribution of brachytherapy sources, calibrations, application evaluation. An autoradiograph is basically what sort of development on a piece of film do you see when you put the autoradiograph out there? And then interstitial sources are going to be something else you're going to be looking at. Remote afterloaders, you're looking at acceptance there, depending on, is it safe to operate? Is it able to retract the source? What are the channels like? Which ones work? Which ones have certain lengths of cable? They could be different depending on what type of procedure you're wanting to run. Source positioning, does it give you the, when it comes out of the afterloader, is it hitting the spot that it should? Source calibration, is it delivering the amount of radiation that, what is that amount? And then, how well does it decay, that kind of thing. You can see the autoradiograph that I was talking about earlier. Commissioning is just checking to make sure that we have the data on this particular machine to model it. In other words, its own signature as to how it's going to be delivering dose. For a linear accelerator, you're going to be looking at central axis depth dose tables. Again, the TPR, TMR, that's something we'll get into a little bit later. Isodose curves, what do they look like? Monitor unit calculations, what are they going to be? And then you can see here the commissioning data that has to be compiled. And trust me, there's a lot of protocols about how several protocols from the AAPM that go through on how to do all of this. They're going to be looking at MLCs, transmission, central axis depth dose, penumbra, that kind of thing. The treatment planning computer is also going to be evaluated because it's going to be taking all of that information as computer files and trying to determine exactly, you'll determine from it exactly what you want to do as far as delivering dose. The linear accelerator is going to have certain things that are checked on it annually, certain things that are checked monthly, certain things that are checked daily. And a QA program is going to allow you to be able to operate to see exactly what it is that we're going to be looking for. And you can see different types of procedures and their tolerances here that you might be looking at daily, and then monthly, and then annually. So it really is going to kind of depend on what sort of unit you have. Cobalt 60, we're not going to worry about that so much. I don't think any of you are going to be working on that, or a radiographic simulator for that matter. CT simulator, again, you're going to be looking more at the diagnostic. Physicists, they'll probably be doing a PMI, or the preventative maintenance. Risk assessment in radiation therapy, what sort of parameters are you looking at? What sort of tests, tolerances for different things? That's something you really don't have to worry about so much. So anyway, the process of doing QA is there. It's to make sure the patient's okay, to make sure you're okay, to make sure that the procedure is delivering the dose that we want delivered in order to be able to treat something. And that's its purpose. I will be coming up with probably a small homework assignment or quizzes. There won't be too many problems over this particular chapter because there's really not a heck of a lot to ask. It's going to be kind of more rote than it will be working out problems. But that's the purpose of QA, and I hope that was somewhat enlightening for you.